We now examine singular points. So remember, a singular point was any point that was not an ordinary point. However, there are two types of singular points. So we consider a singular point x0, and we say it is a regular singular point. Of the differential equation a2 of x y double prime plus a1 of x y prime plus a naught of x y is equal to 0 if the two functions little p of x is equal to x minus x naught times big P of x, and little q of x is equal to x minus x naught squared times big Q of x, where the big P and the big Q are given by the differential equation in standard form. So little p and little q are both analytic at x naught. So a singular point that is not regular is said to be an irregular singular point. So, how can we determine easily whether a point is singular? Now that comes in our next theorem. So we let a2, a1, and a0 be polynomials. If x minus x0 appears at most to the first power, in the denominator of big P of x, which is a1 of x divided by a2 of x. And at most to the second power, in the denominator of q of x, which is a0 of x divided by a2 of x. Then x equals x0 is a regular singular point. So just as in the previous section, we can form a power series solution of a differential equation centered at a regular singular point. This is known as the method of Frobenius. And the theorem we use is called Frobenius's theorem. So it states, if x equals x naught is a regular singular point of the differential equation a2 of x y double prime plus a1 of x y prime plus a naught of x y is equal to 0, then there exists at least one solution given in the form y of x equals x minus x naught to the r times the summation n equals 0 to infinity of c sub n x minus x naught to the n. Or equivalently, summation n equals 0 to infinity of c sub n x minus x naught to the n plus r, where this number little r is a constant that needs to be determined. So the series, as before, will converge at least on some interval 0 less than x less than r, big R. This big R, again, needs to be determined. It is the radius of convergence. Unlike in the previous section where that big R was the distance from the ordinary point to the closest singular point, we'll actually have to find this big R when we find our power series solution. Another key difference is right here. It says there exists at least one solution. So when using the method of Frobenius, it's possible that we only get a single power series solution. Whereas the previous method, with ordinary points, we were guaranteed 2 power series solutions. We will see an example of a case where we get only a single power series solution, and we'll see how to develop the second solution from that. We will consider the differential equation 2xy double prime plus 1 plus x y prime plus y equal to 0. As before, we will always center our solutions about the point 0. Now 2x equals 0 at 0, so this is a singular point. The c, if it is regular, we note that p of x is 1 plus x over 2x, and q of x is 1 over 2x. The power of x in the denominator of p of x is 1. The power of x in the denominator of q of x is also 1. So the degree is at most 1 in p of x is at most 2 in q of x. And so this is a regular singular point. So we guess a solution, summation n equals 0 to infinity of Cn x to the n plus r. Y prime would then be the summation n equals 0 to infinity Cn times n plus r times x to the n plus r minus 1. Y double prime is the summation n equals 0 to infinity, c sub n plus r, n plus r minus 1, x to the n plus r minus 2. We now need to take these three values and plug it in to the differential equation. And that has to equal 0. What we're going to do now is algebraically simplify this. So we're going to distribute this 2x into the first summation. We'll split the second summation into 2 by distributing the 1 in, and then by distributing the x in. We will now combine the two summations that have x to the n plus r minus 1 and the two summations that have x to the n plus r. Notice we also factored out a c sub n from both of them. Now each term in this sum has x to the r, so we can go ahead and factor out an x to the r. Notice we also algebraically simplified the two expressions. Now, we want the first term of each sum to have x to the power of 0. This sum already has that. We need to pull out the n equals 0 term from here. So the n equals 0 term is r times 2r minus 1, c sub 0 x to the minus 1. Then the sum will start at 1 and go to infinity. we are now going to shift the index of this first summation so that it starts at n equals 0. That means that in the summation, everywhere you see an n, we replace it with n plus 1. We can now write these two sums as a single sum. And that has to be equal to 0. Now if we look at this, since x can't be 0, we can divide both sides by x. That means that this sum is 0. So we do coefficient comparison. We have to compare this term with 0, and then that term with 0. So we have r times 2r plus 1 times c naught has to be 0. Since c naught is any constant, r times 2r plus 1 has to be 0. This is our indicial equation. And this gives us the values of r. So this will give us that r1 is 0 and r2 is a half. Now comparing that second term, we have n plus r plus 1 times 2n plus 2r plus 1 c sub n plus 1 plus n plus r plus 1 c sub n has to be 0. So c sub n plus 1 has to be negative n plus r plus 1 over n plus r plus 1 times 2n plus 2r plus 1 c sub n, which is the same as negative 1 over two n plus 2r plus 1 c sub n. Now this will give us two recurrence relations, one for each value of r. So let's start with r being equal to 0. Then our recurrence relation is c sub n plus 1 is equal to negative 1 over 2n plus 1 times c sub n. We're going to have to try and recognize a general pattern. So let's start with n equals 0. Then c sub 1 is negative c sub 0. For n equals 1, we get c sub 2 is equal to negative 1/3 c sub 1, but c sub 1 is negative c0, so this is a third c sub 0. n equals 2. C sub 3 is negative 1 over 5 C sub 2. But C sub 2 is a third C naught, so we get negative 1 over 5 times 3 C naught. Let's look at one more. N equals 3 will give us C sub 4, which is negative 1/7 C sub 3. And C sub 3 is negative 1 over 5 times 3 C naught. So this becomes 1 over 7 times 5 times 3 C naught. So it would appear in general that for the r equals 0 case, we would have C sub n is equal to negative 1 to the n minus 1 times 1 over 2n plus 1 double factorial C naught. Now again, C naught can be any constant. So our first solution y1 of x is equal to x to the 0 times the summation n equals 0 to infinity. Times one plus 1 minus C naught x plus a third C naught x squared minus 1 over 5 times 3 C naught x cubed, so on and so forth. So it's x to the 0 is of course 1, so we wind up with C naught, this should be a C naught up here, times 1 plus a summation n equals 1 to infinity of negative 1 to the n x to the n over 2n plus 1 double factorial. But again, this C naught can be any constant. So let's say it's 1, and we get that y1 is 1 plus the summation n equals 1 to infinity of negative 1 to the n x to the n over 2n plus 1 double factorial. We now have to determine the radius of convergence. Well, 1 obviously converges for everything, so we just have to determine the radius of convergence here. And if you remember from Calc 2, we use the ratio test to do this. So we look at the absolute value, negative 1 to the n plus 1, x to the n plus 1, over 2n plus 3 double factorial, times 2n plus 1 double factorial, all over negative 1 to the n times x to the n. This equals the absolute value, so negative 1 to the n plus 1 over negative 1 to the n is simply a negative 1. X to the n plus 1 over x to the n is x. over 2n plus 3. Right? Because 2n plus 3 double factorial is 2n plus 3 times 2n plus 1 double factorial. So this simply equals the absolute value of x over 2n plus 3. As n goes to infinity, this converges to 0, which is less than 1 for all values of x. So this series converges for absolute value of x less than infinity. But remember, x has to be greater than 0. That was the theorem. So we take this to mean x is greater than 0. So that takes care of the first solution. We now have to look at when r is a half. So when r is a half, we get the recurrence relation c sub n plus 1 is equal to negative 1 over 2n plus 2 c sub n. So now we have to do the same thing. Start with n equals 0. c1 is equal to negative a half c naught. N is 1. We get c2 is equal to negative a quarter c1, but c1 is negative a half, so we get 1 over 4 times 2 c naught. When n equals 2, we get c3 is negative 1 over 6 c2, so we get negative 1 over 6 times 4 times 2 c naught. So in general, c sub n, negative 1 to the n minus 1 times 1 over 2n plus 2 double factorial c naught. So our second solution, y2 of x, will be x to the half times c naught x to the 0 minus half c naught x to the first plus 1 over 4 times 2 c naught x squared minus yada yada yada, which is x to the half times c naught times 1 minus a half plus 1 minus a half x plus 1 over 4 times 2 x squared minus yada yada yada. So we get x to the half c naught times 1 plus the summation from n equals 1 to infinity of negative 1 to the n x to the n all over 2n double factorial. But again, c naught can be any variable, so we set it equal to 1, and we take our y2 to be x to the half plus the summation n equals 1 to infinity of negative 1 to the n, x to the n plus a half all over 2n double factorial. Once again, we need to find the radius of convergence. So we take the absolute value, negative 1 to the n plus 1, x to the n plus 3 halves, all over 2n plus 2 double factorial. times 2n double factorial all over -1 to the n, x to the n plus a half. Which equals the absolute value of negative x over 2n plus 2, which is the absolute value of x over 2n plus 2, which, as n goes to infinity, converges to 0. That is less than 1 for all x. So we'd have a radius of convergence, absolute value of x less than infinity. Once again, though, x has to be greater than 0. And so we say x is greater than 0. Now that we have our two solutions, we can write our general solution. C1 times 1 plus summation 1 to infinity, -1 to the n, x to the n over 2n plus 1 double factorial, plus C2 times 1 plus summation n equals 1 to infinity, of -1 to the n, x to the n plus a half over 2n double factorial, which is valid for x greater than 0. This process is even more tedious than the previous process we looked at. We now look at the differential equation xy double prime plus y is equal to 0. Again, we'll center our solution about 0. This is a singular point. P of x is 0. Q of x is 1 over x. So this is a regular singular point. So our solution will have form sum n equals 0 to infinity of c sub n x to the n plus r, y prime, sum n equals 0 to infinity c sub n plus r x to the n plus r minus 1, y double prime, sum n equals 0 to infinity c sub n plus r plus r minus 1, x to the n plus r minus 2. So we'll get x times the sum n equals 0 to infinity cn n plus r minus 1, x n plus r minus 2, plus sum n equals 0 to infinity cn x to the n plus r, and that whole thing equals 0. And just as we did in the previous example, we're going to have to algebraically simplify this. So first thing we're going to do, distribute this x through. Let's now factor out x to the r. We need to write the first sum so that the first term, x has power of 0. So we pull out the n equals 0 term. Then the sum will start at 1 and go to infinity. Shift the index of that first summation. We can now combine the sums into a single summation. And that equals 0. So we again have to form our indicial equation, and then our recurrence relations. So the indicial equation will be r times r minus 1 is equal to 0, which means r is either 0 or 1. To form the recurrence relations, we have n plus r times n plus r plus 1, cn plus 1, plus c sub n is equal to 0, and so c sub n plus 1 is equal to negative 1 over n plus r times n plus r plus 1 times c naught. So let's start with r being 0. Then cn plus 1 will equal negative 1 over n times n plus 1 c naught. Notice that n cannot equal 0, so our summation would have to start with n equals 1. This, of course, means that there is no c sub 0 term. I'm sorry, I don't know why I wrote c0 here. This should be cn. So when n is equal to 1, c2 will be negative 1 over 2 times 3 c1. My apologies. This is not correct. C2 would be negative 1 over 2 c sub 1. When n equals 2, we get c sub 3 is equal to negative 1 over 2 times 3 times c sub 2. But c sub 2 is negative 1/2 c1, so we'll get 1 over 2 times 3 times 2, c sub 1, and let's write that as 2 squared times 3. For n equals 3, c sub 4 will be negative 1 over 3 times 4, c sub 3, which will be negative 1 over 2 squared times 3 squared times 4, c sub 1. Let's write this as 1 over 2 times 3 times 4 times 2 times 3. Or rather, let me write it this way instead. 4 times 3 times 2 times 3 times 2. N equals 4 will give us C5 equals negative 1 over 4 times 5, C sub 4. So we're going to get 1 over 4 times 3 times 2 times 3 times 2 times 4 times 5, C1, which we will write as 1 over 5 times 4 times 3 times 2 times 4 times 3 times 2, C sub 1, and so on and so forth. So our first solution x to the 0 times, there is no C0, so it's C1x plus minus a half C1 x squared plus 1 over 3 times 2 times 2 C1 x cubed plus minus 1 over 4 times 3 times 2 times 3 times 2 C1 x to the 4th plus so on and so forth. X to the 0 is of course 1, so we can factor out that C1, and we're left with x minus 1/2 x squared plus 1 over 3 factorial times 2 factorial x cubed minus 1 over 4 factorial times 3 factorial x to the 4th plus so on and so forth. And so this is C1 times the summation n equals 1 to infinity of negative 1 to the n minus 1 x to the n over n factorial times n minus 1 factorial. And since C1 can be anything we want, we set it to be 1, and we get the summation n equals 1 to infinity of negative 1 to the n minus 1 x to the n all over n factorial times n minus 1 factorial. Now, we have to consider the case where r is equal to 1. This will give us that Cn plus 1 is equal to negative 1 over n plus 1 times n plus 2 c sub n. So if n is 0, we get c1 is equal to negative 1 over 2 c sub 0. N equals 1, we get c sub 2 is negative 1 over 2 times 3 c1. So we get 1 over 2 times 3 c sub 0. Let's rewrite that as 3 times 2 times 2. Starting out to be the same as when r was 0. N equals 2, c3, negative 1 over 3 times 4 c sub 2. So we get negative 1 over 4 times 3 times 2 times 3 times 2 c sub 0. And I'll leave you to verify that if we keep going, we're going to get the same pattern as we got when r was 0. So y2 will be x to the first power times c0 minus a half c0x plus 1 over 3 factorial times 2 factorial c0x squared minus 1 over 4 factorial times 3 factorial c0x cubed plus yada yada yada, which equals c0. I'm going to pull out, and I'm going to also factor in that x, so we get x minus a half x squared plus 1 over 3 factorial times 2 factorial x cubed minus 1 over 4 factorial times 3 factorial x to the fourth plus yada yada yada. And I'm going to stop there because if we come back up, that is identical to this. Remember, C0 is any constant set it equal to 1. We get the exact same thing. So we do not get a second solution out of this. This means we have to form a second solution. And we do this using reduction of order. So it's going to be y1, which was the summation n equals 1 to infinity, negative 1 to the n minus 1, x to the n over n factorial times n minus 1 factorial. Then it's times the integral of e to the negative integral 0 dx all over this summation. I'm not going to rewrite it. Squared dx. E to the negative integral 0 is just 1. So we can write our general solution. Factor out the y1, so n equals 1 to infinity, negative 1 to the n minus 1, x to the n over n factorial times n minus 1 factorial times c1 plus c2 times the integral of dx over this summation squared. And I leave it to you to verify that the interval will be x greater than 0. If you're feeling particularly brave, you can attempt to actually evaluate out this integral. I would not recommend it. It's a very long and very tedious process. I will just leave my answer in this form. For algebra simplicity, choosing your center to be 0 is always the right way to go. However, if 0 is a singular point, you can see you have a little bit more tediousness to go through. In my opinion, this method, the method of Frobenius, is still algebraically simpler than trying to center your solution about a point other than 0. That concludes this lesson. I hope you've learned something, and we'll see you in the next one.